Hello folks. So to describe any semiconductor device or any semiconductor, we often use the concept of band diagram, and we use these two bands to describe most of the physics of our device. And the band which is labeled, which is colored in pink over here, this is usually called the valence band, also denoted by letter EV. And this band in green is typically called conduction band, denoted by this letter EC. And we say that above your conduction band you have states available for carrier. Similarly, below your valence band you have states available for your carriers. And while in this energy between your conduction band and your valence band, you cannot have carriers in this energy level. And these conduction band and valence band are separated by this energy gap, or this forbidden energy level where you cannot have any carriers, and this is typically called as the band gap, also denoted by EG. So what I want to derive in these set of videos is give you understanding of where does this band diagram come from and what defines this band gap. So I want to use two different models to describe this. The very first is a very simple model using bonds, and I'll describe that in this video. And I'll also use this chronic penny model, which is a more quantitative model. It uses a very small amount of quantum physics or Schrodinger equation, but I'll derive it and explain it to you. And both of these I'll use to explain, how does this band structure come from, and why do you have these continuous availability of states above your conduction band, similarly continuous availability of states below your valence band, but these are separated by this band gap where you cannot have any states. So let's start with this bond model, and I'll start with a simple atomic structure of this Bohr model of an atom, which I'm sure all of you know from your high school physics. And I'll use the element silicon, which is the most prominent semiconductor material when these silicon atoms are arranged in a lattice. But initially, if you look at just one atom of this silicon, so I know that silicon has an atomic number of 14. And from again my high school physics, I know that if I have an atomic number of 14, these electrons would be arranged as 1s2, 2s2, 2p6, 3s2, and 3p2. Sometimes this instead of writing this as 3s2, 3p2, people write it as 3sp4 as well. So if it's already, people assume that it has already bonded. But in any case, so we'll have two of our electrons in this first orbital. Then you'll have 8 of these electrons in the second orbital, and then you'll have 4 of these electrons in this third orbital, which is partially filled. And we also know things like this radius of each of these orbital is given as a function of n square, and similarly the energy of electrons in this orbital is given as is inversely proportional to n square. So this is you might remember this 13.6 eV is comes from a hydrogen atom. So for a hydrogen atom, you in fact have this shell has an energy of 13.6. This has 13.6 divided by 4, or around 3.4 eV. Similarly, this one has 13.6 divided by 9, or around 1.51 eV. For the case of silicon, you need to substitute this dielectric constant, which is 11.7. Similarly, the mass is not m0, it's more like 0.3 m0, and we'll discuss why that is. So in the case of silicon, this is multiplied by approximately 0.3 and divided by 11.6 squared. So for the case of silicon, these electrons in your valence shell, or your third and your outermost shell, have energy of around 50 MeV. So you see that these electrons in the valence shell are not as strongly bound, and these are the one which are responsible for most of the properties, these valence shell electrons, as we know from our Bohr model as well. So now what happens when you instead from going from an atom, if you go to a lattice? So what I want to understand is what happens, or what really causes from my this very well understood picture of Bohr model that I learned in my high school, that what happens that I go from here, which is this individual silicon atom, and if I go over to this side, that is if I go to a lattice, why do I instead of getting these individual states, I get more like this band structure, where I get a continuous density of states available in these band, and then another continuous density of states available here. Similarly, a continuous density of states available over here, while there are no density of states, so there are no states available in this forbidden region, which I call as band gap. So why do I going from this lattice, of going from this individual atom into this lattice, why do I get this band gap? So a very good starting point is to take these atoms and bring them close together and see what happens. So let's assume we have one of these silicon atoms, and excuse my poor drawing over here, and I have these individual states. So I'll have something like this. Let's talk about one electron over here. So let's assume we have one electron, and this is in my valence shell. So it will have let's also denote it by a wave function. So it will have a wave function which is like this. And now what happens if I have another of these atoms? So I'm assuming over here that I have another of this atom, and this is far separated by a large distance. So if that is the case, these wave functions do not interact. But now what happens if I bring these atoms close to each other? So if I bring two of these atoms close to each other, these wave functions now start to interact. And now what I have is a situation where I could have this electron, and it could be either in this particular state, or it could be in this particular state. And both of them are similar states, but by Pauli's exclusion principle, I need that I cannot have one electron in these two identical states. So what I need to happen is, or I cannot have these two electrons in this one single state, because Pauli's exclusion principle says that essentially if you have these two separate electrons, they need to have their own states. So what needs to happen is that this two individual states from these two atoms, they need to split up into this two different states. And as you know that from simple wave mechanics, you typically get something which is a constructive interference, and you get something which is a destructive interference. So you get these two different states. So now assume that we assume this case that you had two of these atoms coming close to each other, and let's consider the case where you have now let's say another of these atom coming very close to each other. So now you'll have three of these states, and this was assuming one electrons per atoms, but we just saw that our silicon that has four of these electrons in our valence state, so you'll have four per atom, and then if you have n number of atoms, you will have this splitting of one of these states into these 4n states. So if this was if this was the case for 2 atoms, so you'll see two of these states. If this was the case for 4 atoms, you'll see 4 of these states. Similarly, if you had the case of these 4n atoms, so you'll see 4n of these states. So we could say 2n of them over here, and then 2n of them over here. So we are already seeing that instead of having these discrete states, we are now getting these states which are multiple of these states. So instead of just having three particular shells in our one atom, we are now getting 4n of these states. And assuming a crystal has anywhere between 10 to power 23 or those kind of numbers associated with a crystal lattice, so you'll get a lot of these states. So we are already seeing that there's some continuity emerging over here. So let's explore it further, and this is explored further in this chart over here. So if I have just one individual atom, I have this picture where I have these discrete states. But now when I start to get multiple of these atoms close together and arrange in a lattice, what I see is that as I bring them closer and closer to each other, these states, they start splitting up into multiple states. And then depending upon how many atoms I have, so I'll have multiple of these states over here, and even more multiple of states over here. And I start to see that if I make n sufficiently large, what I'll see is these lot of states over here, and a continuous density of states over here, and these are separated by this splitting, which I'll call as a band gap. And this depends how close I bring these n number of atoms. And typically you'll bring them close enough such that they form a lattice, and you have this spacing of lattice constant between your atoms, and that would determine what is this band gap, and where exactly your conduction and your valence band lie. So hopefully we got some idea in this video, and I'll expand on that in the next video using another model, how do we derive this band structure.